hacker who was the Syrian cyber army hacked into 6 root certificate authorities and stole their stuff. And he dumped 2 of them publicly to prove it and said he had 4 more he never told us. The Syrian Electronic Army had this. And at that time, the Syrian Electronic Army was one 19-year-old in Syria, loyal to Assad. But he said they didn't have any segmentation. They didn't even put serial numbers on their certificates. They didn't have default passwords.
I'm really sorry.
Which is pretty believable. I mean, nobody audits you before you become a certificate authority. You just put up a website and start selling certificates. You could just be some idiot in his basement using Windows. A guy contacted me on the internet and said, you should bring in your class to come see my server setup. So I went there. His server setup was one computer, half the size of that, running Windows NT that had never been hacked, connected directly to the internet, under like a sink. And he was hosting websites and email on that. He said, I've been running this for 10 years. People are paying me for hosting, and this never got hacked. It's fine. It's just, and there's a student of mine that went and got like a domain name for $5bucks.com. And then, of course, he got hacked. He's like, well, I think I have a pretty good idea what's at the other end of that name. There are these really cheap services, and there's a reason why they're really cheap. Anyway, all right, so I think we're up to the right time. Good. So let's talk about Windows. Windows. We've finally done a lot of Linux. We've done as much Linux as we're going to do this course. I don't think we'll be going back. Now we're going to do the same stuff on Windows. So Windows is much more complicated. So let's talk about some basic concepts. APIs, DLLs, and PE files, and then heaps, threading, DCOM, exceptions, and debuggers. And then we'll hack something using old school game hacking to get started hacking Windows and debuggers. So Windows 32, which is the only thing we're going to worry about here, 32-bit Windows code. The API is the application programming interface. If you want to do something on Windows, like send a packet out the network card, you are not authorized to do that. You are not allowed to touch any hardware directly from user land. Only the kernel can do that, and you are not allowed to put code in the kernel. The only way to put code in the kernel is to install a device driver. And so all you do, you cannot send anything directly out the network card. All you can do is ask the Windows kernel to please do that for you by making an API call that calls software Windows wrote, or the person who put in a device driver wrote. So that's the game. It's a series of DLLs, dynamically loaded libraries. This is a feature that Windows, as I mentioned in the projects, you have to put the no pi switch or the static switch, the static switch is the main one for this, in your Linux code to make the simple kind of code we've been hacking, or else Linux tries to use dynamic libraries also, which complicates the assembly code. But Microsoft has been using dynamic libraries for a long time, so that if multiple programs use the same library, like network calls, they all share one copy of the library in memory instead of each of them having to load their own copy. So it saves RAM and load time, but it is a security risk because it means not all the code is in one place. And you loaded code from potentially untrusted sources. Yeah?
The Ubuntu 14 something, the version, the GCC, the no pi option is not, you cannot use the no pi option.
I am not sure about that. The question is whether Ubuntu 14 uses the version of GCC. I don't know. I know that it moved from Kali 2016 to Kali 2017. They upgraded GCC, I think, to a version which you now had to put in the -no pi. There is, if you have old versions of GCC, I don't think it recognizes the switch because it doesn't have the ability to produce position-independent executables anyway.
Yeah, I think it uses the old.
Yeah, and that's when I originally wrote the class, everybody was doing that. People were not making pies on Linux, which means most Linuxes were not using address space layout randomization. Now apparently they are, and the more modern Linuxes have it, so you have to turn it off if you want to do a hack that cannot withstand.
So the older version assume the no pi is there.
Yes, I think that's essentially right. The older version just assume everything is no pi. Yeah. All right. So anyway, this is now a set of DLLs. And the device, the dynamically loaded libraries change, of course, with every update and with every service pack. Yeah.
There was a chat.
Oh, a chat. Oh, good. Thanks for telling me. Let's see what's coming up in the chat. Can you please repeat the questions? Yes. I'm trying to, and I appreciate your reminder. All right. So, All right, that's good. All right, so every process has to dynamically link to the DLLs, and the Windows API changes a lot. So here's an API call to make a window. You have an HWID, which is your handle to this object that's created. It's going to be a window. This will create a window, and then you put in things like the title of your window and other code numbers like how big it's going to be and where it's going to be. And then it creates an object, it's a window, and you have a handle to the window, so you can then do things like close the window, resize the window, and stuff later. That's what an API call looks like. So these are DLLs, pre-compiled code that came typically from Microsoft, although other people can write them too. And then they load as needed. You can see them with Process Explorer. Here's Process Explorer, and here's service host.exe, and you can see down here all the DLLs it's loaded. And too bad that projector isn't very clear, but anyway, you see each DLL that's loaded, and we'll look at it live a little later. So portable executable files is the general container for all Windows executables. Everything is in the portable executable format for EXEs and DLL files. And these can be loaded on 32 or 64, and you can see them with PE view. So here's the import table for Notepad. Notepad, actually, there are many different versions of Notepad, amazingly enough. The single text editor comes in Windows. So you can open Notepad in PE view, and it will just show you the structure of the PE file. So here is the import table. Most client software, like Notepad, to run in userland, has a lot of imports, which means it loads functions from DLLs. So that it's using some function from ADAPI, Advanced API, from kernel, from GDI, from user, and so on. So the person who wrote Notepad made a call of a function in this library, in that library, in that library, and this will let you see its connection to all those library modules. So when you load Notepad, it then has to connect to all these DLLs. And if the DLLs are already in memory, it'll connect to them. And if they're not, I can close that if we have to, but I think they're going away. Yeah, maybe I better close it. It's locked. It's unlocked anyway, so. Yeah, people like to hang out there and make a lot of noise. Anyway, so all right. So your PE file has certain sections. Text is the assembly language instructions to execute, which is kind of a funny name for it, but that's what it is. You have global variables, import descriptors, these are imports. So imports are functions you use in a library. Exports are, if you're a library, functions you offer to other people to use. So consumer code like Notepad and Word has a lot of imports, but not many exports, because it's not intended for something else to use that code. These are resources, and there's relocation data, which is used to relocate the program in memory. So DLLs have a base address where they are intended to load. And I'm not quite sure how this works out with address space layout randomization, but I think this is actually a virtual address inside each program. But anyway, two DLLs might have the same base address and be used by the same EXE, and therefore they can't both have that location in the memory space of that executable, which is a virtual memory, not a real memory. So in that case, one of them has to be moved, and that's what the relocation is. They have to alter the code to move it to another location. So it is a little slower to load, and an adjustment process has to happen where things change to map to the new location. So that's why I say imports are functions you use in another function like a library, and exports are services you offer to other programs. So normally, you don't export anything unless you are a library. So here's the Notepad.exe imports. So it uses get token information and reg set value and reg query value and all these functions like Windows API calls. And you can see the import address table. It has to bring in these values and then jump to those locations to use these libraries. And when you load the program, at the time of loading, it makes these connections to the actual location in the RAM of your system to make it all work. Here's ADVAP API. Exports. This is the Microsoft Advanced API library, so it's got something called, I can read them better here, abort system shutdown, access check, add access allowed, and so on. These are all little functions that do something with the API. So as you've seen before, if you try to load a program and it cannot find a required DLL, you get this crazy message, cannot find ftd2xx.dll. I used to see this all the time in Windows 98, but I still see it in modern versions of Windows. The reason why you see it so much is because when programs are uninstalled in Windows, the uninstaller does not know whether to delete the DIL or not. That's why sometimes it'll pop up a box, X4P792.DIL is no longer used by this program. Should I delete it? And they expect you to know if some other program is using X4P792.DIL, and if you click the wrong box, it deletes it, and now some other program will stop working because you deleted that DIL. So it'll drive you mad. And what's funny is Linux solved this in 1975 by having something called a link count. Every program that uses something makes a link to it, and it has a link count in the properties of the object, and every program that's deleted lowers the link count. When the link count falls to 0, it's okay to delete it. But Microsoft has not yet figured out how to do this. Anyway, that's the game here. Another thing that can happen is you might have installed software, but it fails to update the path variable, so it cannot find the DILs in the installation directory, so that's another thing that tends to happen. Anyway, Stuxnet used this. Stuxnet, to attack the Iranian isotope separators, was on a USB stick, and it would have a program here, which would have an icon, and then it had a DIL right here. And this is a DIL injection vulnerability. This is a modern way to do it. If you load a DIL, it will hunt for the DIL through the path. So you can make what's called a companion Trojan. This is a system DIL that is used to draw the icons in Windows Explorer. It should have fetched this from C Windows System 32. Let me get rid of this. This thing keeps popping up. All right. Anyway, it should have loaded that from C Windows System 32, but if you put one on the USB stick, it will load from here first because it's earlier in the path. So you can make a DIL which will be mistaken for the Windows System DIL and loaded and used. And that's what happened. By having this DIL on the stick and this file on the stick, it tries to draw this icon using the routine in that file on the connection machine. It was bloody awesome and very easy to do. And that's how almost all malware works, by DIL injection. You put your malware in a library and you trick some program into loading that library.
Can you like input the system to get rid of it without using the DIL on the USB?
You say, can you reboot the system to get rid of this? And no, I do not think so. The only thing you could do, I think, is change the path variable.
No, I mean after the USB.
Oh, after it has happened with the USB, then it just depends on what it did. And I think this one used a 0-day to install a rootkit. So you're hosed. Rebooting won't get rid of it. The loaded DIL will be gone, but it could have done some damage, which would be persistent. And that's what happened in the case of Stuxnet, of course. All right. So there's a relative virtual address. Every Windows program believes it is running at this address, 400,000 in headers. I don't know why, but that's by convention. You may have noticed in what we've done in GDB, all your Linux programs think they're running at 0804.0000. For some reason, they choose to have a relative address like a virtual machine where they think they're at that location. That's mapped by the system to some other location, which is random by ASLR for using. So anyway, this is called a relative virtual address, and it's used to rebase DILs. So here's an example. Physical memory might be at 300,000 to 500,000, but the programs both think they're running 400,000. And there's a table in the operating system to tell it where they really are. So OllyDbg, the actual code section always starts near 400,000. You open your code debugger, you'll see numbers like that. 401,000 at the start. That's the memory loads there. And you can see the memory map in the debugger. And you'll find the text section, just like we did in GGB, with info files, info file map. Now, in our Linux programs, there was one heap, and we did some heap overflow exploits. Windows has a much more complicated heap structure. They have many different heaps. Each DIL sets up its own heaps. So there are heap corruption exploits, but they are very confusing. There's a thing called the look-aside table and a bunch of advanced complicated things about heaps in Windows. And then there's threading. Every process is divided into threads, and each thread is what actually gets processor time. The idea here is your program can be doing several things, and it can keep one part of it moving even if other parts are going slowly. So you can see them in Task Manager. So here's my machine. I booted in and look at Task Manager. I'm looking at 41 processes, 677 threads, and 18,000 handles. That's how it is. You have processes, one for each program that's launched, and there's system processes, or 50 or 60 in a modern version of Linux. Each process has many threads, and each thread has many handles. The handles are those values that point to things like windows, input sockets, and such. So you can see them all here. That's what handles are, just pointers to things that are being used. You can see them all in Process Explorer. Here is a Process Explorer window looking at the some process, Explorer.exe, the one that draws the desktop, and it shows me its addresses, and it shows me all the threads with thread IDs, which are all part of the same process ID. And then down here, it has at the bottom, I think, some information about handles. But anyway, it tells you, you can now look up a lot of information, far more information than you probably want. All right, now here's why things get so crazy on Windows. Microsoft Windows was designed to make money, right? Unashamedly right from the start. Their whole purpose is to make it efficient for you to write and sell code and make money with it. So they invented this thing called DCOM and DCE-RPC. The idea here is once you write some code that does something, you should be able to market it and reuse it in another environment. So here's the game. If you want to write a program, you don't have to write it. You can pay people to write libraries and then use their libraries. So you get them to write COM libraries, and then you write a little Visual Basic shell to tie it together, and you can have an application even though you don't really know how to program. So these things are called COM objects. They can be written in any language, and they interoperate seamlessly. But the various languages that you use do not have the same data formats. So you have to have an interface description language file to go with your COM object, and that looks like this. It will tell you that you have a short function here that says type 2 and type 1, this is a type 1 element pointer, and so on. It's like the header of a C file that specifies what variables you have and how big they are. That's what's in the IDL file. And so you'll pay somebody to write a COM doing something and give you the IDL file, and then you just plug it into your Visual Basic module and you have your game or whatever you're trying to write. So that's the game. The return values and arguments go in the UUID, also called a GUID, which is Universal Unique Identifier and Global Unique Identifier. And there's a fundamental rule for all Microsoft names. All Microsoft names say the opposite of what they are. The text section does not contain readable text, it contains instruction code, and the global unique identifier is the same on every system. It's not unique. I don't know why they do this, but that rule helps you remember almost every Microsoft name for anything. The Microsoft systems boot, there's 3 stages of boot, and each one of them is labeled as the opposite of what it is. Anyway, so you can load a COM directly as a DIL, or you can launch it as a service, and then it will just run in the background in the operating system, and many people can share it. That's what services.exe does. And if it runs as a service, it's more stable and secure, but slow. Although I might argue about the secure part, because almost all services run as system, more powerful than the administrator, because the services have to launch before you log in. So they can't be tied to any user account. Many of them. Anyway, so in-process calls loaded into your process is 1,000 times faster than calling a COM interface. But you go through another process. And by the way, I should mention, although it's not in your book, if you load a modern version of Windows ever since Vista and go to netstat-an, you will find that it has about a dozen high-numbered ports listening on 127.0.0.1. So there are a bunch of internal processes that go through the network card back to the same machine. And that might seem okay, but the latest thing Vince Tabiso has been proving from Google is that it's really not okay, because if you access a website to do updates and you maliciously change the DNS response to resolve that website as 127.0.0.1, you can take over local listening sockets from the internet. And he's been doing this to software like crazy for the last several months, and finding everybody thinks it's harmless to just loop back through the interface to 127.0.0.1, and it's not really so harmless. It's not as different as putting it on the real internet as people think it is.
How do you do that?
You change the DNS resolution of your server to resolve to 127.0.0.1. And now when they think they're connecting to your server, they're actually moving back to your machine. It's a DNS rebinding, he calls it. So you have to trick them into going to a domain you control and then put malicious content in your DNS server. So here's the Service Control Manager. It runs as services.exe. It's in your task manager. It's always running. Okay, so Microsoft's priority here is to make it easy for you to resell your software in a larger context. So you write like one game with some cool module, and now you say, I'm just going to sell this module to other people, use it in other products. So here's the game. So you can write a program, a module that was intended to be loaded in one exe space. And then you can make it available as a service so all the processes on that machine can share it. And then you can connect it to a network socket and share it over the internet, all with the same code. And this is often done not by the original developer, but by like the marketing team when that developer is long gone. So code that was originally supposed to be inside one product is now just shared over the internet. This is how you get the security disasters. This is pretty much how the whole internet got so insecure. You have horrible things like Telnet. Originally, Telnet was to take a keyboard here and connect to a computer there, no internet, no nothing. So it just sent the characters one by one down the wire, and that was fine. Then people invented networks, and they just put Telnet over TCP/IP all over the place because it was the logical way to improve the functionality, and they weren't thinking about the security. And that's what's happened here. So you can take your code and move it, make it available to all the processes on the machine or all the processes on your network without changing the code. And that's what people do. And this is what RPC is, Remote Procedure Call. You have an endpoint mapper listening on port 135, and it does a request here to see if you will offer service to that port. And it maps to UUID values. So when you do the request, it will tell you, you have a 34 UUID, here's the thing, it gives you these code numbers, say, I'm offering these services, and here's the interface language to talk to these services. This is what's on 135, which is many, many spreading worms use this. The reason it's insecure is not that there's anything intrinsically wrong with it, but the one port is used for a whole library of services. And the services were developed by this process I described. So it is very likely that some of them have old security vulnerabilities that they wouldn't have if they'd been freshly written for this purpose, or indeed designed for this environment. They were often designed for a limited environment where they would not be under attack, and then just ported to this public environment without rewriting. So a lot of components depend on RPC. You can just go to Remote Procedure Call and see how many things do. Many, many parts of Windows require you to run RPC. You certainly have to run it on domain controllers and other Windows servers. And it is quite dangerous. And that's the point. Code was designed for one environment and reused in a much less trusted environment over a network. So there are a whole bunch of tools to fuzz, find vulnerabilities and exploit them, recon, fuzz, and so on. You can do this with Spike and other tools. Okay, now another thing is tokens and impersonation. Microsoft has to keep track of who you are. And it does that with a 32-bit integer, like a file handle. This defines your user rights. So here I am Sam, then there's system, and there may be other things on here. You can see it in Process Explorer. You can go to a process, and you'll find that this WinLogon process has threads. Some processes here are running as systems, and others are running as SAM, because that's the process that displays the logon prompt. So some of it has to run as system to display before I log in, and apparently some of it runs as SAM after I log in. Some threads have one privilege, and some threads have another. These tokens are just sitting in RAM, and they're easy to steal and replay, and you're doing it in the 124 class. So you can create threads and copy any token you want to them, and there's typically tokens just sitting around to steal. It's one common way to escalate to domain administrator. And then there's exception handling. Remember, there are IRQ lines in the hardware of the motherboard where you can say, I have an immediate request to service something like the network card, and it will stop whatever it's doing and do that. But there are many other kinds of exceptions, like divide by zero, attempt to use non-executable memory, attempt to reach an invalid memory location. If those things happen, the processor generates an exception. then the normal sequential code stops and it goes to the exception handler to figure out what to do. And this, by the way, is what leads to the Spectre and Meltdown vulnerability that came out a few months ago. The exception process takes some time. So if you do something illegal, the exception is triggered, but by the time it's triggered, you have already executed several more instructions in the pipeline. So several forbidden instructions have already happened before the exception handler takes effect in a modern processor, and that leads to Spectre and Meltdown. But even before Spectre and Meltdown, the exception handler was a juicy target for attackers because the exception handler is pretty easy to mess with. You can view it in Immunity. You'll see a series of addresses. These are going to ones Microsoft wrote in NT-DIL, which is the heart of Windows NT. So if you can overwrite the pointer to the SEH chain, you can change all the exception handlers or ones you wrote, or you can overwrite the default exception handler, which is the one that takes place if you don't handle it yourself. See, if you write code like a game, you can write, if you don't write any exception handlers of your own, it will just go to the default one, and that will go to the operating system, and it will pop up operating system messages like system crash, Dr. Watson, blue screen of death, that sort of thing. You could write custom exception handlers inside your app, so your app will not crash. It will handle an exception internally, which is pretty cool. But if you overwrite the default exception handler and don't provide your own exception handlers, it will go execute that code. Yeah?
So there's a way to tell the processor not to take any exceptions?
Yes, if you handle the exception yourself, it does not get passed to the operating system. Now this applies, by the way, I have to be more careful when I said this applies only to user land exceptions. The blue screen of death is a kernel land exception, and that's beyond your control typically, usually. So that means you cannot recover because the kernel died. But so I should have included that in the same category. These are user land exceptions we're talking about.
So if you somehow manage to get into root or kernel, you can do whatever you want.
Well, yeah, exactly. If you have administrative privileges, you could install something with kernel and run it there like a rootkit. But that requires escalating the system, and it is a whole other world. We'll do some of that a little later. That's good. All right, so you are debuggers. The way you do all this stuff is you run your code in a debugger so you can see what's happening while it's running. Just like in Linux, we use GDB for everything. SoftIce is an old powerful one, but I've never used it. WinDbg is the one that came from Microsoft. It's the one recommended. Most Microsoft-rated developers use it. WinDbg can debug the kernel. Now, to properly debug the Windows kernel, where you would do something like put a breakpoint in the kernel and stop kernel processing, you have to have two computers because the one where you've frozen the kernel is frozen. It can't do anything. So Microsoft designed WinDbg to use two computers connected with a serial cable. And this is an old 25-pin serial cable, 25 or 15 or something. Those things don't even exist on modern hardware. So what you have to do is pay $300 for a professional USB to old serial adapter, or get a Chinese one for $10 that doesn't work and causes the blue screen of death every few minutes, which is by far what most people do, which will all drive you mad. Now, in earlier versions of my malware analysis course, we actually set the kernel debugging with a simulated serial connector in VMware, which can be done, but it is very painful. However, now we have LiveKD. LiveKD is a Mark Rusinovich product, and it lets you do kernel debugging with one machine because you cannot put breakpoints or stop the kernel, but you can examine the kernel by just triggering a memory dump and then analyzing the dump. The dump just copies all the memory in the kernel to a file, and then you view the file. So you can at least do some inspection of the kernel with only one machine, and that's awesome. Now, OllyDbg is the standard for malware analysis and hackers for years. It was very popular, but it appears to have been abandoned. So the code base was rewritten into Immunity Debugger. OllyDbg version 1 is wonderful, still works fine. They upgraded to version 2, which is unusable, horrible, beyond belief. You will actually lie to you. I've never seen a product like this. I don't understand why it was ever released. You list the DILs, and some of them are just not there. I thought I was going out of my mind. I was using it, trying to follow a textbook, and it says, now find this DIL, and it's not there. It's just lying. So wherever you do, don't use OllyDbg version 2. But you can use Immunity. Immunity is based on the Olly code base, and it's maintained in modern. The early version of Olly and the modern version of Immunity are both fine, and they're both very similar. Same instructions work pretty much. All right, so here's the joy of Immunity. And let me just check and see if we're ever going to get to the iClickers, because I thought I had some, or maybe not. Okay, I thought I had some for this slide. We're just going to talk about, I'll just demonstrate this. So let me see what my time is. 1:38, okay, we're on time. So let's talk about Immunity. And I'm just going to demonstrate the project 8A here, which is where you hack into PuTTY. You could use any Windows application, but I just chose PuTTY, and I'm going to download so you can get the exact version of PuTTY I'm using. Other versions of PuTTY are a little more complicated. This version is a few years old. So you start Immunity. And it looks like I already had Immunity going. I'm going to stick with that one because it's already got my, what's going on here? Okay, I can't close it for some reason. Exit. Okay. This one's already got my, okay, it's already got my fonts set up. If you start Immunity, it will be little tiny fonts you can't see. And I've blown them up a lot bigger, although I must say they're still pretty miserable on that projector. Feel free to move closer if you like, but I don't think I can make it any bigger than this. All right, then you load your file, which is C Administrator's Desktop PuTTY. This is where you do most of your exploit development in Windows, right here in the debugger, just like you did most of the other stuff in GDB. GDB is just a command line version of this, and this should be familiar. On the left, you have the assembly language instructions, push and move and call and stuff. And over here, you have, just like in GDB, on the right, you have the readable stuff, like get version exe. Microsoft Windows API calls can be recognized because they often end in A or W, and they often have EX for the extended version. You get used to their naming convention. That's a Microsoft Windows API call. So this loader is going to find out what version of Windows you're using and decide whether it can run or not at the start, the default thing. This is the registers. This should be familiar territory, EAX, EBX, ESP, and EBP, the start and end of the stack frame. EIP is down here. Remember, every Windows program thinks it's running at 400,000. So here it is at 400,000 and something where the code is. Down here is just a hex dump pane where you can dump anything you want. It'll show up like a Wireshark with hex on the left and ASCII on the right. And this is the stack, showing you what objects are on the stack. This will return to NTDIL. The program is ready to launch. This program is not running. One of the most confusing things when you start using OllyDbg or Immunity is when you launch a program and it stops. The same thing happened in GDB. If you try to run the program or connect it over the network or something, it's paused because it loads into RAM and then stops before the first instruction. This is intentional to give you a chance to set breakpoints and get ready. If you want to use the program, you have to run it. And you run it here. This little magenta arrow will run it. Now the program launches and it opens a window. It opens this window in PuTTY, and you use PuTTY. Now it's waiting for input from me. So if I put in input, name some server to connect to, and then open. If it's the first time I've ever connected to the server, it'll ask me to download the host key. I've already done that. And now it'll give me a login as box, and now I can put in a name and password and connect over SSH. This is all the functionality I care about, is showing that message. We're going to mess with that. So let's go back to here and find out how that message appears. So you can right-click here, and you can search for all referenced text strings. This is quite handy. It gives you another box with tiny little letters. I'm going to make them bigger. Right-click Appearance, Font, System Fixed Font. That makes them about as big as I can make them. These are all the strings that are referenced in this program. This search function is kind of frustrating. You have to start by going to the top because it only searches down from the current position and it starts almost at the end for some reason. Now you can right-click and search for text. So I can search for login as and say OK, and I will find item not found. Yeah, that's what tends to happen to students, and I never have found a good solution. It likes to do that. It's lying. It's in there. Maybe if I close this box and reopen it, something better will happen. I get many students stuck at this point in the project. That thing won't search, and I never have understood why. You just have to go try it again, and it'll eventually start working again. If anybody can figure out what's going on, I'd be interested. I thought I had finally figured it out by making you go to the top of the window, but now here it is failing again. Hacking tools tend to be like this. Let's try not going to the top first and see if this works. Search for text, log in as. Nope, still doesn't find it. Okay, let's see if somebody in the chat knows what's going on. This is a very common problem, and I've never gotten to the bottom of it. Unchecked case sensitivity. Yeah, I can try that. There is a space between log in and as. Yeah, but I know that's not it. Those are good ideas, but I know they're not going to work because this is remembering what I did before. You know what I might have to do is reload the program. Let me try that. But first I'll do what you guys want just to prove that I'm not talking through my hat. If I get rid of case sensitivity here and search, still tells me that it's not found when it is totally there. So let's reload the program, debug, restart. One thing is I let it run to the end. Maybe that didn't. Maybe the fact that it wasn't running caused a problem. That would actually make some sense. Maybe that just the text was from the Windows operating system, not from Immunity, because the program wasn't running. That would make some sense. I'm making stuff up though. Search for all reference text strings. You know, I think that might have been it because these are not the same. I think that might be what happened to my students too. They closed the program, then searched for strings, and when you close the program, you're not seeing the same thing. These are now PuTTY messages. Okay, now I feel a little better. So now I go to the top. So actually, that's my latest theory. If you see PuTTY things here, you're in the right place. Now you search for text, and it's login as. And here's the first one, login as. There are two of them, and you could breakpoint them both and find out which one of the breakpoint works, but I happen to know it's the second one. I'm just not going to mess around. It's this one here, 41C B6E. Click on that and press F2, and that will put a breakpoint there. It turns red. So now, when it tries to execute this instruction, which uses that string, it will break. So now I can close this, and I can run the program. And here, I go to ad.samsclass.info just to have a server that ledgers with SSH. And now, it opens the box and it hits the breakpoint. So this is now, you can see, it's asking login as, it's going to push this value, 467C7C on the stack, and that value points to this string. This is Immunity, making it easy. And in fact, you can see that value by right-clicking here and click follow in dump, immediate constant, which is the number referenced by that instruction. And now it puts it down here, and you can see this is login as right there. So you can now modify the message. There's a couple things you can do. Let me start by doing it at the assembly code level. If I click on that and press space, it lets me change this command. So I can change 467C7C to 467C7D. Now, when I assemble it, the modified instruction might be different in size than the original instruction. And if that happens, it will fill the notch. That's what that checkbox is showing. So I assemble. It didn't change it. It changed this number, so now it points to 7C7D. Now I cancel because I don't want to do it anymore. And notice this now says login as, because I changed the value of this by 1 byte, so it skipped the first letter. Now, if I run the program this way, and look here, it prints login as instead of login as. So I've now modified the program. Now, I could save it this way, but I'm going to save it another way. So I'm going to get back to clean start. Whenever you get lost in Immunity, you do debug, restart. That will relaunch the program and get you back where you were. Now, I can run to that breakpoint again. That's one way to go. I think I still have my breakpoints. We're going to see. To get back where I was. Unable. Oh, I spelled it wrong. Okay. Debug, restart. I could also remember the address and feed it in with go to location. But I'm going to try and do it this way. ad.samsclass.info. Yep, now I hit the breakpoint. By the way, I didn't mention it much here, but these corners are really important. This tells you whether it's running or paused, and this tells you what I just did. This says breakpoint at putty.address. So that tells me I've hit a breakpoint, and you can see I'm back where I want to be, where I'm going to be ASCII login as. So now instead of changing that number, I'm going to change the stored data. So I right-click, and follow in dump, immediate constant, and now down here I can change this text. I highlight the text I want to change, right-click, binary, edit, and now I can go up here and just change it to like your name. I can't change the number of bytes, not easily, although I could actually probably put it in null byte and it would probably accept it as Terminator, but it's best if you don't change anything here. Now I've created a modified version of the program, and I could run it, but bad things happened when I did it that way before. I want to save it now before anything else happens. It is tricky to save your changes in PuTTY. In an earlier version of this project, I actually gave up and used HXD to manually edit the save program instead. But I figured out just this morning how to do it. You have to go to the right pane here and save the file, which is copy to executable file. That creates a window showing a hex version of the modified program here with your name in it. And it's got all the rest of the program up here. So now I can right-click on that and save file. And that's going to be PuTTY YN for your name on my desktop. So now I've made a modified file. And if I can get to my desktop, I've got problems with the boxes from that Zoom product getting in the way. Okay, now I got a problem with VMware. VMware doesn't draw the desktop very well, so it's leaving old junk in the way. Resizing fixes that. Now I got another problem with VMware, that it doesn't show me the desktop properly. I've gotten used to this stuff. There's my PuTTY YN. All right, now if I run this one and connect, now it has your name instead of the other Chrome. So that's what I wanted. I can now make a modified version. And so that, what I just showed you, is project 8A rather. And 8B is putting malware, because you might as well go all the way. So now you can do what we just did was, this is the kind of EXE hacking you do to cheat at games. We now change the operation of a program like changing a message. We could just as well change the number of points you get for doing something in a game. This old-fashioned script kiddie hack. And now the next thing is put in malware. So in this one, if I can ever get the extra junk out of my way on my screen, you now know we can change that number. So what we can do is, instead of pushing a different value here or changing the text, I can change this to a jump that will jump and execute code, much like we did in Linux. But now I need to find a place to put the code, and the way you do that is use this product called LordPE. LordPE lets you open portable executable files and see their sections right here. So the PuTTY has text, RData, data, and resource. And you can add another PE section called new seg. And what you do, you give it some size, and you can make it executable and readable and writable. You specify whatever permissions you want for it. And now you go into Immunity, and you change that instruction to jump to the new section, 484,000. Find out where it is and just jump to it. And then you just go to Google MSF Venom and make some malware. I used HXD here, there. I just went into MSF Venom. You used it to make Linux malware, but you can make Windows malware with MSF Venom just as well. So this is raw Linux malware or Windows malware, 328 bytes. So all you have to do is put that in the new section. And there might be some way to do it inside Immunity, but I didn't know, so I just used a raw hex editor. I just formatted the malware to fit this way, and now you can just paste it into HXD, a raw hex editor. You can change programs byte by byte. So paste in that junk. It comes in as this red junk. That is the egg, the malware that will do a listening shell on 4444, just like before. Now save that, and now you have a Trojan version of PuTTY that will, when you run PuTTY, it'll start listening on 4444, and anybody can connect and take over your box. So this is how you make Trojan code. Now, someone mentioned in the projects, of course, you have to have no antivirus on the box that's doing this. That's why I gave you a Windows 2008 to use. You can easily use your own Windows machine, but you have to not have any antivirus because all these Metasploit payloads are detected by antivirus, of course. But that's it. This is how you make Trojan programs. And it's really quite easy with Immunity. And I thought it was very good to have this sort of script kiddie, old-fashioned hacking stuff to get used to the basics of Immunity. This is sort of like the first Linux project or two when all you do is print you win by redirecting code. You learn the basics. After this, we'll start attacking a server. There's this great thing somebody wrote called Vulnerable Server that's sort of like an email server, and it has like 10 vulnerabilities, runs on Windows, and you can totally practice finding vulnerabilities and hacking, and we'll do that. Then we're going to move up to using more modern code. This one has address space layout randomization, so we will overcome that with return-oriented programming. And then we'll defeat data execution prevention also with return-oriented programming. And then at the end, we're going to do a heap spray. I didn't go all the way, but I mentioned earlier, address space layout randomization protects you by moving things in memory. One defense is to just try your attack hundreds of times until you get lucky, because Microsoft didn't put enough entropy in it. Another attack that gets through it is the heap spray. The heap spray is a web-based attack. You open a web page, you run JavaScript. First, you design your attack. You have an egg, like I have there, maybe a few hundred bytes that you got from MSF Venom or something. Then you put a NOP sled that is really big on it, like 10,000 bytes. Then you make millions of copies of it in JavaScript over and over and over until you just fill all the RAM with it. Then you just jump at random. And you have a very high chance of hitting one of those NOP sleds, and you win. It doesn't matter that you don't know where your code is. You just fill all the RAM with your code. That's a heap spray. So it's possible to do. You'll do it here. You'll just fill it with code full of your name or something and show that it's everywhere in RAM. These are the things that slowed down the white hat hackers for about a year when Microsoft put in the new defense of address space layout randomization and data execution prevention in Vista. That year, nobody won at the Bowne contest. They had to downgrade to XP. It took the good guys about a year or two to figure this out, and then they found ways to punch through these new defenses. So those defenses made all the XP and earlier malware stop working, which at a stroke, which was very good. But nothing is perfect. All right. So are there any questions about anything? Yeah.
About that Trojan party, if somebody put it online and you download it, or your antivirus software detected.
That's a yes. Yeah. That question is whether your antivirus will detect this poison. This particular Trojan, if you were to put it online, antivirus will stop it because we got the shellcode from Metasploit. If you wrote your own shellcode in assembler, then probably it would not be detected. And if you got a good obfuscation program like Veil Evasion, it might be able to hide it from antivirus, although I think Veil Evasion is leaked. And if you want to get away with this, what you do is you just learn a little programming and write your own packer and your own unpacker, or you pay $30 to someone on a Russian forum and they will write a packer for you. Because it's easy enough to do. All you do is write a little code in C or something that makes a little unpacker. Do something, anything you want, like XOR every third byte with F. Now it's scrambled. All you have to do is write a code in front that will undo that. And as long as nobody else has used that exact code, antivirus is helpless. So you just have to write anything like that. So if you don't know enough coding to even do that, you can hire someone in Russia for $30 to do it for you. And that now you have a sort of poor man's zero day. It's not really a zero day because the technique is not unknown, but it is something antivirus won't catch. And if you are worried about the heuristic detection in antivirus, all you have to do is program a delay at the start of your code, because this is what I learned from the internet when I went through a project where I wrote Python code to sneak past antivirus, and Bobby Tables on Twitter contacted me and told me the way the heuristic detection works is it launches your code in a virtual machine and looks for it doing nasty things, but the user can't be expected to wait forever. So it only waits about 10 seconds. So all you have to do is do something harmless for 10 seconds and then do your malicious thing, and the heuristic engine will not catch you. Now, to be fair, they did catch obvious things like sleep. If you try to sleep for 10 seconds, I'll notice that. But all you have to do is like download a file or calculate something big. You come up with some way to waste a few seconds before you do the nasty thing. And as long as that technique of wasting a few seconds is not on their radar, you sail through. This is like, this is like profilers at the airport trying to see if you're a terrorist. All you have to do is not look like what they expect, and you're getting through. They're just humans that wrote the antivirus, and they know what the current attacks are, and they watch for that. You just have to do something that is not on their list of the threats they understand, and off you go. The whole idea of antivirus is kind of insane. That's why F-Secure is the antivirus that makes more sense, because it implements whitelisting. Whitelisting is so much more logical. If you just enumerate all the good products and only let known good things run, that is achievable. Trying to enumerate all the evil in the world and recognize it and block it is kind of hopeless, because there's an ever-expanding number of evil products. And F-Secure, if you install it on a Windows machine by default, it will do that. It will only let known good software run. And that's what iPads do, and that's what iPhones do. And that's what Macs do when you freshly buy them. And that is a really strong defense. Anything that's not on a list of known good apps just won't run. That's much better posture, but it's most people are not willing to put up with it. They want to be able to write their own code. They want to be able to download stuff. And as soon as you can do that, then there's no real way to stop it from being malware. So, any other questions? See if I got anything coming in online. Looks like I don't see anything.
Is Immunity or Debugger voice for this?
Immunity and Olly are both the same as far as I can tell. Yeah, they're both good. Dashboard Immunity is the debugger of choice. And here, could you leave the audio on for the post-lecture Q&A? Yeah, but I think this is it. And any more of that coming? I think not. Okay, well, we're just going to go up to the lab or work on things here. I don't think I can leave it on after this. All right. So I'm going to stop this. I'll post this video. Go ahead and do those projects. Now, actually, I thought I had some Cahoots. Let me see if I can find those. Those would be fun things to do. We've got time. My thoughts on IDA as a debugger. As far as I know, I'm not an expert at IDA, but as far as I know, IDA is useful to disassemble code, but as far as running it, putting in breakpoints and stuff, I don't think it's really well designed for that. I think it has only some rudimentary features. Let me see if I can find some Cahoots. I thought I had some about this, but I didn't see a reference to it in my slides. But let me check. Cahoots. If I have them, now would be the time to use them. I'm thinking perhaps I forgot to post them for this, though. No, that's right. I got some Cahoots. I don't know why I didn't have them earlier. I must have loaded the wrong version of my lecture. So let's do some Cahoots. That'll wake people up. All right. All right. Good.
Have you played with Radar?
What's that?
Radar? I don't know if I'm saying that right.
Radar?
Radar, R-A-D-A-R-E.
Radari, oh, Radari, yeah, Radari 2, yes, I don't know how to say it either. Radari 2, I used it, and it's pretty fun. I was thinking of adding an extra credit project with it. There are a few things. There's like better than GDB. They have like more automatic features. If you did easy CTF, they had an environment like that. If you're in, I thought about it. There's also some visual, graphical versions of GDB. They all seem terrible. That's why I stuck to the old command line, because the ones I tried were hard. Radari 2, though, makes it pretty easy to modify Linux executables and run the modified version inside the debugger. So I did a few projects with it, but I didn't bother adding it to class yet. I might, it's a well-known product. Let's see. I'll wait another 10 seconds and see. Oh, we still got people coming. Then I'll go check the information storage unit. Here it is. Good. Okay. Huh. Should have shown these earlier, but better late than never. Okay, another 10 seconds. All right. All right, there's one. which file contains precompiled library. Okay, those are DLLs, good. That's a good name. All right. The set of functions Microsoft provides to access the kernel. Okay, that's the API, Application Programming Interface. The overall format for all Windows executable files. Good. And you should just zip in. Okay, those are portable executable files. They're portable in the sense they move through memory with ASLR. All right. Which section of a PE file is used for rebasing? It has the relocation section. Which section contains machine code instructions that should be executed? The text file. Text section. All right, what section contains icons? Okay, resource section, good. Okay, so it is space and Bill M, which might be a real name, and Ling, which might be a real name. I got a few more of these, so just keep going. So it should be, I'll close this and run 6B. Here, all right. I think 12 is as many as I get. I'll wait 10 seconds. Okay. Okay. For these. Okay, what portion lists the entry points into a disk? Can I export them? It's not the imports. You export is what you offer to the world. And those are the functions I offer. What memory section is a single block in Linux, but many pieces in Windows? Okay, that's a heap. Right, which has the largest number when running Windows? Many handbooks per thread, many threads per process. Right, what's the allocation unit for CPU time? The threads are what actually gets CPU time. Everything has to break into threads and they move forward. All right. I got Bill M twice, Crystal Court, and Technofile, a good name. All right, let's do one more of these, which is here. There we go. All right, wait 10 seconds. Okay. All right, the inputs and outputs of an object. That's the IDL interface description. 128 bits. UUID. All right. What happens if you divide by 0? Okay, that's a structured exception handler. What's on port 135? That's remote procedure call. All right. Which one is 32 bits? Token, although I think there might be a handle to a token that's 32 bits. Anyway. All right. Which debugger can debug the kernel? That's WinDebug. All right. Which one had a good old version and a bad new version? Okay, that's Ollie. All right. So Bill M times 3, Kaz, and Crystal Cook times 2. All right, people will have to tell me their real name if they want to get points, or whatever name you're actually signed up for quizzes for, in case you're using some pseudonym. And I'm going to try and issue some kind of certificate for people to finish this. I think it ought to just be an online badge. I'll have some pictures up there. I haven't quite thought of what to do yet. But that does seem like a good idea. I guess it should be available to other people who take my classes anyway. But especially for you people who aren't getting any other kind of credit right away, that would seem like the thing to do. Anyway, a lot of people I need to know who you are, like Space and Blaine and Kaz and Technophile and Crystal. The only one I know, Ling is probably a real name, and Bill M is probably a real name. The rest of these people aren't getting points unless I have a little more information. Aha! Extra credit. What do you get for winning the Kahoot? Yes, you get extra credit. Technophile. Okay, good. I now have Technophile's name. Good. Yeah, and it only matters if you care about the grade or whatever you're going to call it. Okay, good. Number 32. Okay, I have his name. Good. And I'm me. Oh, good. Thank you. I know who Kaz is. Good. So now I've identified everyone except Crystal. That might be a real name. I didn't think so. Crystal something. Not a person in the room. All right. Crystal may be online, but I don't know who they are. I'll see. Crystal Corp, okay. I'll send it that way to my grader and see if she can figure it out, but probably not without something closer to a real name. Crystal Corp, aha, is in here. Yeah, look, Crystal Corp is in here. Send me an email. Oh, good. Okay, good. Crystal Corp is coming by email. Good. Okay. Any other questions then? Now I'm going to stop the share. Okay. And you can work here if you like.